about some piecewise functions, okay? So this first slide really explains kind of what a piecewise function is in general. The notes did a pretty good job, but I want to make sure we go over this and hear this out loud. Piecewise functions are these graphs that look weird, like the one on the right. One side of this is a horizontal line. Then all of a sudden, on the second part, there's a parabola. They don't touch each other or anything else, but because they're graphed on the same coordinate plane and they're in the same color, what we're saying is this is actually the same graph. What I've done is I've broken this graph up into pieces. The left side is defined by one equation. The right side is defined by another. So when we look at piecewise equations, they are functions that are defined in pieces, at least two. You can have as many as you want, meaning you could have a piecewise function that has 15 different parts. No, I won't make you graph or really look at one that big, but it is possible. Okay, we could have that many different equations. Standard piecewise function form. You start with the leftmost equation, meaning just like every other graph, we work from the left to the right. And the first part of this, you get this f of x or y equals, and you get this really big bracket symbol. And the first part of these things will tell you equations. I'm going to put the dot, dot, dot down this way because it's however many equations our graph has. Then you get a comma usually, or a semicolon, or a bunch of spaces. It's a semi-uniform notation, but depending on who types it, it can look slightly different. But you're going to get some sort of break, and then you're going to get the domain that graph exists on. Now we got to remember when we talk domain, these are x values. So it's the x values that we see that portion of the graph. So I'm going to tell you the equations for these two up here. The leftmost equation, this is a y equals 5 line. You got to think back to our rational features or when we found asymptotes, okay? That's like half of a horizontal asymptote. But this equation is at y equals 5. The second part, this is a y equals x squared. I know because I created it, okay? If we actually went to, hey, how could you find those equations from the graph? That gets a little bit more complex, and we're not diving that deep yet. We're just talking about basic structure, okay? Because I wanted to show you is when you write it in piecewise notation, the leftmost equation is the y equals 5. This f of x down here, this is the y. So this is y equals, the only thing you need to write inside here for the equation 1 is the number 5, because its equation is y equals 5. The second equation is y equals x squared. We would just write x squared in there. Those are the two equations that we see for this function. However many, we have 2 because this graph had 2. We're talking about kind of looking from a graph to writing the function down. Now, when we go through, we write domains. That can get a little bit tricky, but we know that means to the left forever. So that to the left forever is negative infinity. Where does that graph stop? Like if you had to pick your pencil up, you would draw it and then you would stop right here, right? So this graph only exists from negative infinity to this point down here at 0. Now, if we look at y squared, y equals x squared, it starts at 0 and goes this way, and it's going to go out to positive infinity. Takes up everything. Now, what we need to look at, which is going to be tough to see because I think I covered it up, so I'm going to erase these dots. The graph looks like it exists, both graphs look like they exist at x equals 0. Because we put some sort of mark there on the graph. But only one of them includes the 0. So what we've got to remember is on piecewise graphs, it becomes especially important. Where we switch from one graph to the other, we'll see these bigger dots, either filled in, which is what the bottom one is, or not filled in. The filled in dot means that it's included in the domain. where you would see if we were writing with inequalities, we'd see the little bar underneath our inequality, or we would see our square-ended brackets if we were writing an interval notation. If it's not filled in, this is where we, in inequalities, we wouldn't see the line underneath there, or you would see rounded parentheses on the end of it. Meaning, if I were to write the domain for 5, it's negative infinity, and it stops at x equals 0. So it's negative infinity to the 0. Does this one include the 0 or exclude the 0? Is that dot, can you tell from the back, is that dot filled in or open? Let's zoom in on it. Now we can kind of see it. Is that dot filled in or not? Look at compare them. That bottom one looks like that one's filled in. This one is open. This is not a great graph for that. Usually we try to make them bigger because we try to avoid that confusion. What I get at is if you ever sketch one, it's not a bad thing to make your open circles obvious compared to your closed circles. Okay, and I will try better at the ones that we have in the past or in the future. But that 0 is open, meaning that this is going to get a rounded bracket because it doesn't include the x value of 0. When we look at the x squared, that was the 0 all the way to positive infinity. It gets the square bracket because this one had the dot, and let me fill it in even more, make it more obvious. You would probably see something more along the lines of that, overemphasized. That make it more apparent? Okay, because that's what you would see on the graph, a little bit more exaggerated than normal. So this is the equation that you would see that represents this graph. When you look at it, it's broken down into pieces. You should be able to see some obvious differences through the graph, okay? We don't do a ton with making the graphs. We do more with looking at the equations and the situations and understanding that they're piecewise and being able to evaluate given functions, okay? So this is the one that I gave you on our Desmos page. So which equation should I see first? Like, what equation is the farthest left on my graph? It should be, if this is set up in the right order, this x plus 4. It should go from negative infinity to positive 1 and have an open circle. That should be this graph right here. You can see this one's a little bit better drawn. It has an open circle here at x equals 1. This is the line y equals x plus 4. And when you go through, you can kind of check this. You could plug numbers into this that are inside this range, meaning if you plugged in 0 into this equation, the graph says we should get an answer of 4. If we plugged in 0, 0 plus 4 is 4. You'd be able to find every point that you could put on this line by plugging in that x value into the equation. It'll tell you the y that's supposed to come out. Same thing happens for each one of these. 2, y equals 2 is a horizontal line, like a horizontal asymptote. The number at 1 should be included, but the 4 should be excluded, so that's closed and open. This is another line. And this one goes to infinity because it's got an arrow. That's how we know the x goes to positive infinity. This one was negative infinity at that arrow. And it's included. The 4 starts at x equals 4, goes to positive infinity. You could write some points out from each equation and sketch graphs, but we won't do a ton with sketching graphs. But a lot of times you may want to match the equation to a graph. Meaning that if I want to make sure that this is really x minus 5, pick a number between 4 and 5 and see if that point is actually on the line. Meaning, let's pick x equals 6. That's between positive 4 and positive infinity, and plug it into this and see what we get. So that's 6 minus 5, so it tells me the y value should be 1, meaning this graph should have a point, x equals 6, y equals 1. We come in here and we look. It's really hard to see, I know. But this is 6, and if we count up, it's even tougher to see, but it's split in half. That is 1, because this is 2, this is 1, and it looks better on your screen than it does on mine while you're looking from the back of the room. So that's one way you can identify, hey, which graph should this equation be? You can plug numbers into those equations that you're given and start matching things up. As soon as you get one that doesn't work, you know that that graph isn't matched to that equation, vice versa, and you can ignore that one and move on to the next. Okay? So that's kind of our basic structure of these things. We are taking functions and putting them on pieces of the x-axis so we can represent different things. One way that might work, we're going to do a little word problem together. Okay? This is one absolute real example of this. Anybody work? How's overtime? You like overtime? I know when I got paid by the hour, I loved overtime. I was doing the same work, but I was getting paid a whole lot more to do it, right? So paying things is one way that piecewise functions come in. I believe our tomorrow's examples that are thrown on the Canvas page do a lot with parking. Your cell phone bill runs on a piecewise function if you have metered data. Lots of things run on a piecewise function, meaning you use more, you pay more. Or even more, if you use more, you tend to pay less per item, even though you're paying more overall, right? If you try to order 10 shirts online, you pay $20. But if you order 100, they may give them to you for $15 a shirt instead of $20 a shirt because you're ordering more. That's kind of a piecewise pricing scheme. But let's look at this and see if we can kind of figure our way through this. So you get paid out $8 an hour. If you work more than 8 hours in a day, you get paid time and a half. So let's make a table to represent this. So let's go 0, 1, 2, 3, 4. Oh, we should probably not start at 0. Let's start at 1 because we're going to run out of space with this table. And so this is our time, right? And this is going to be how much we make. This is our pay. Now, what we make in a day is a function of how long we work, right? You work 7 hours in a day, you get paid a certain amount. So we get paid $8 for each of these hours. So that means if we work 1 hour, we make $8. If we work 2 hours, how much are we going to make? We make 16 because we make 2 8s. Then this is 24, 32, 40, 48, 56, 64. What happens as soon as we pass that 8th hour? All of these changes, if we looked at it, right, we can see it really easy that this is going up by 8 each time. But as soon as we pass right here, are we still going to go up by 8? And we're going to make time and a half. What does that mean? Well, we get paid $8 normally. What happens as soon as we work more than an 8-hour shift, we get paid that and half of that again. So time and a half is $8 plus an additional $4 for each one of those hours. So now all of a sudden we're going to start going up by 12. So now we end up with 76, 88, and I could keep doing this, right? So question, even though this table stops, since the way this problem is set up, well, we'll talk about it when we get to the equation. Let's graph it. Because what I want you to see here is it's tough to see, but you do end up with a slightly different looking graph. So let's see, 10, 20, 30, 40, 50, 60, 70, 80, 91. It's not going to be perfect, but I'm going to create a sketch of this thing because I want you to show that this looks very similar to what we just saw, just not as pronounced. So let's graph this. So these are hours on the bottom, amount that we make on the top. And let's graph our points. 1, 8, 2, 16. And then what I'm going to do is I'm going to kind of cheat because this graph's not going to be perfect. 864 is about right there. These things should make a straight line. And the reason I connect this with a line, those of us that have worked, you can't see that line. Can you get paid for half an hour? Like if you work 6.5 hours, do they round it up or round it down? Or do they pay you exactly what you worked? They pay you exactly what you worked. If you clock it, if you're punching a time clock, they pay you down to the minute. So this is a continuous function as it goes through. You can connect the dots. All those points are going to end up on this line. And I can put them in now because 3 was 24. Then we ended up with 32, 40, 48, 56. I was pretty close with my slope. Those are all our hourly pay dots, but we can get paid in between there because you could work 7.5 hours and you're going to get 7.5 hours worth of time at $8 an hour. Now what changes though is all of a sudden when we go from 8 to 9, we're not making $8. That slope of that line is actually going to increase on us because we're going to make more money because we jump from 64 to 76. And then all the way up here to 88. And I'm going to graph this in a different color. Let's use green. Most of the time it's really tough to see, but that little corner there, that's not normal. We can't write that with a normal type of equation. To get that into our equation, we have to actually write this as a piecewise function. So this over here will be piece 1. This over here will be piece 2 because we have suddenly changed the way we're calculating our rate. So when we go and we actually write a rule for this, we need to find the equations for these things. Now I think we could reason our way through these without doing this really mathematically. Let's say our X is going to be the time worked. How do we find an f of X is going to be our pay? For every hour from 1 through 8, what did we do to the numbers 1 through 8 to find out how much we would make? Did we multiply? Did we add? Did we subtract? Did we divide? Like, how did we figure out that 8 hours would be $64? We took the 8 and we multiplied it by $8 because that's how much each one of those hours was worth. So we took $8 and we multiplied it by the time we worked. This is the function that defines our pay for the first 8 hours. And we're looking at total pay. And where it gets a little tricky is when we start talking about what happens after that. Because when we go to write an equation, and we'll get to domain in just a second. When we go to write an equation for the second part, when we work 9 hours, does it change the way that our pay is calculated for the first 8? No. So when we do this second part with this real world style piecewise, we still make this same amount of money for the first 8 hours. But what's good about this, instead of writing this as an equation, how much do we make once we hit the 8th hour? We know that we make $64. That's exactly how much we'll make for 8 hours. After that, we're adding to it. Our rate has changed. All of a sudden in here, we started going up by $12 an hour instead of $8. So that means for each one of these hours after this, we add $12, But do we multiply that by all of our hours? No, because remember, this counts for the first 8 hours. We can take our hours and multiply the first domain from it. I'm sorry, to subtract the first domain from it. Now, when we talk domain and range with this thing, this one starts at 0 and goes to 8 and includes it, because our first 8 hours, that's how we get paid. Reason we don't include 0 is because if you don't go to work for a whole week, does your boss even bother sending you a check? No. Once you work 2 minutes, technically he's got to send you something, right? But if you don't work at all, you never step foot in the building to actually work, you don't get paid. The 8th hour, if you work exactly 8 hours, this is how you'll get paid. You'll get paid exactly $64. But once we go past 8 hours, we get paid with this function. Now, we talk about the end of this. Is this how we'll get paid for forever? Because the domain on this one's weird. We don't see it on the graph. But how many hours are in a day? You get 24, right? And the way that this is worded, when should that domain end? Well, technically, you can't work more than 24 hours in a day because there's not more than 24 hours in a whole day. So this ends at 24. This would be our equation with that. Each one of these is a little bit different. Okay, and you'll see those when you get into tomorrow's work. You got to kind of reason your way with them and reason your way through them. One of our main practices with this is going to be stuff like this. Okay. Now these things are. I pulled this straight from our Delta Math assignment so that it would match what you would see when you go to do this. Because a lot of times the struggles with this have to do with what this means rather than anything. So this down here is using function notation. Function notation is telling you that if you put an X into this, it wants to know what the Y is. So if I give you this graph and I ask you to find f of 6, what this question is saying is if we look at x equals 6, what is the y value that's on the equation? So if we look this way, and we drag this line to 6, which you won't be able to actually drag a line on your computer screen when you're doing these, but you can, I think you can visualize this. It wants to know at 6, where do we intersect the graph? Well, we trace up here and we hit here. All of these should be whole numbers, pretty much. And it's asking me what this number is over here. So the answer to f of 6 is 5. F of 2. So we're going to take our line and we've got to put it at 2. This one might be a little trickier. So at 2, we hit the very end of this equation. Can you see that one? What we need to look at here is at 2, am I really touching that graph? Is that circle filled in or is that open? That's open. So what happens is that 2 is not really included. If you ever get one that only hits, like this one only hits an open spot, it doesn't really touch the graph. This one has no solution. It doesn't hit the graph anywhere there, okay? So if anytime you cross an open hole, it's really not touching the graph. If you cross one, like if we came over here though, we looked at -1, it looks like it hits 3 times. But 2 of those spaces are open, meaning if I asked you what f of -1 here was for this one, -1, a line goes through those 2 open holes, but it touches this dot right here. at -2. So since I do have one spot that's filled in, even if it's just one dot, this one would be -2 for the y value. It's asking you what y value comes out of it. Let's see what the last one says. F of 5. So if we drag our line over here to 5, there's only one spot there. We're touching on the x-axis. So that means its y is 0. So it's asking the y that comes out, that one is 0. Everybody get that? Read the graphs. The other main assessment type that we'll be looking at this is plugging into these things. This is the one that will throw everybody off, okay? So what you have to do with this is you have to determine which equation to use based on the number that we have. So let's do this f of -4. So just like before, these are x values. You need to figure out which one of those this lies in. So is -4 less than -3, equal to -3, or greater than -3? -4 is less than -3, meaning it's going to fall into the first equation here. What you would do is you plug that x into the first equation and you evaluate. So we get -1 squared minus 3, which is 1 minus 3. So we should get an answer of -2 for that one. Same thing with all these others. -3. -3 is equal to -3. So that means I'm going to use this -1. This one's tricky because is there anywhere to plug in the -3 into that equation? No. Anytime you're just given a number without an x, that's always what the answer is. Anytime you're just given a number, that's always what the answer is. Anytime you see an x in one of the equations, you've got to plug it into that equation to find the answer. -10. -10 is definitely less than -3, so we're going to use the top equation again, and we're going to go -10 plus 3 squared minus 3. So that's -7 squared minus 3. So let's see, that's 49 minus 3, so we should get an answer of 46. Hardest part of this is looking at your x and picking which equation to use. You're only ever going to use one equation for each x. You've got to pick which space it's in, okay? Depending on what we're given here. So here we get an answer of -3 for anything that's equal to -3. If it's not -3, our x is, then we get the answer of -4. So remember, these are x values. Is -2 equal to -3? No. So that means it's this top one. One's -4. Is -10 -3? Still no. So that means our answer is just -4 because it falls into the first equation's realm. 10 is still not -3. So that means it's the one that's not -3. So our answer is just -4. And finally, -3. Is -3 -3? Yes, it is this time. So now our answer changes to -3. That one was pretty, there's not a lot going on in that one algebraically. It's more the reasoning, but it's all about determining, is that x value in which specific range is that x value in? And that tells us which equation to plug it into to find the answer. If you're just given a number and there's no x, like we did with this -4, -3, -1s, those are the answers. You don't have to do any algebra with them.